We're going to continue with chapter 6 and exponential functions, and we're going to focus specifically on exponential growth and decay functions in section 6.4. So this is pretty similar to what we saw in the last chapter, or last section rather, but we're going to see a little bit different way to write our two functions down. So the first type of function we have is an exponential growth function. And it's very important that you have this part in your notes with each thing labeled. So a function of the form y equals a, and then in parentheses, 1 plus r raised to the t, where a is greater than 0 and r is greater than 0, is what we call an exponential growth function. So this y part here is your final amount, okay? A is your initial amount. R is the rate of growth, and it's important here, notice this, in decimal form. So a lot of times they're going to give it to you as a percentage, and you have to be comfortable rewriting it as a decimal. So that individual R is the rate of growth. The 1 plus R would be your growth factor, and then T represents the time. So lots of times they're going to say something like, okay, you have a population of 50,000, it's growing at a rate of 3.2%. What is the population in 10 years? So that 3.2% has to be converted into a decimal, 0.032, when you're using this formula right in here. Okay, so it's important that we're comfortable changing values from percentages to decimals in order to write the exponential growth equation, or decay equation, which we're going to see in a little bit. But this is very, very important. Make sure that you have this down with every single part labeled. So I'll give you a couple seconds more in case you need to do it. All right, let's look at our first example. So the inaugural attendance of an annual music festival is 150,000. The attendance Y increases by 8% each year. Write an exponential growth function that represents the attendance after t years. So that function is, remember, Y equals A, and then in parentheses, 1 plus R raised to the t power. So when we're writing this function, Y equals our initial amount. How many are we starting with? Well, in this case here, we're starting with 150,000. So 150,000. Then in parentheses, we always have 1 plus when we're talking about growth, because 1 would mean it's staying the same, but we're increasing it by 8%. So you have to think to yourself, okay, what is 8% as a decimal? 8% as a decimal is 0.08. So then in parentheses, we're going to have 1 plus 0.08, and we're going to raise that to the t power. Can't close my parentheses. Doesn't want to write over there. There we go. And you can simplify this. You can combine what's in the parentheses to get Y equals 150,000. And then in parentheses, 1.08 raised to the t power. Okay, so if you want to simplify it a little bit, you certainly can do that. And that's our function right there. Okay, that represents an initial amount of 150,000. We're increasing by 8% each time. We're raising it to the t power. Now we want to know how many people will attend the festival in the 5th year. So that 5t is equal to 5 here. So all we're going to do is we're going to plug 5 in for our equation. Y equals 150,000. Then in parentheses, 1.80 raised to the 5th power. Now, just like in the last lesson, you have to do that 1.08 to the 5th power first. You can plug it all in the calculator if you use parentheses at the same time. But remember that 1.08 to the 5th is being done first. You end up getting 220,399.2115. 220,339.21. Now, keep in mind, we're talking about how many people, and it says round your answer to the nearest 1,000. So if we round that to the nearest 1,000, that's just going to be approximately 220,000 people. If it said round to the nearest person, it would be 220,339. It said round to the nearest 100, 220,300. But it said round to the nearest 1,000 there. So we have approximately 220,000. All right, so you're just using that formula that we saw in order to write the exponential growth equation. We'll try this in class. Let's look at the same idea here for decay, except notice the difference between growth and decay is that our decay function has a minus there. So it's going to be 1 minus because we're declining. So growth functions will always have a growth factor or a factor that's above 1, and decay functions will always have a factor that's below 1. All right, and that rate of decay, once again, has to be in decimal form. So the only difference from our growth function, which remember was y equals a and then 1 plus r to the t. I didn't write so nice. Try and write that a little neater. 1 plus r to the t. That was our growth. Now decay, remember, as we see down below, is 1 minus r to the t. So when we have a factor that's above 1, it's a growth function. Below 1 is going to be a decay function. Same things though. A is your initial amount, t is your time, okay, y is your final amount. So let's take a look. We want to determine whether this is an exponential growth or an exponential decay function. So the key thing in determining whether it's exponential growth or exponential decay is we want to take a look at our y values here and what's happening here between our y values. We always want to think of it in terms of multiplication. And in this particular case here, you're dividing by 3 or you're multiplying by 1/3. So because you're multiplying by a value that is less than 1, this represents a decay factor. Okay, we're going down. Our y values are going down. They're getting closer and closer to 0. In example B here, we see that we're multiplying here by 2. 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. So because we're multiplying by a value that's above 1 here, this would represent a growth factor. So it's all about looking at your y values and determining whether or not you're getting closer to 0 or you're getting further away from 0. If you're getting closer to 0, it represents decay. If you're getting further away from 0, it represents growth. Same idea even if you were to go into a negative direction. Let's look at example 3. Example 3 says, determine whether the function represents exponential growth or exponential decay. Identify the percent of change. So when you're looking at the percent of change in this part, you want to see how far from 1 you are. So remember, if it's above 1, it's growth. If it's below 1, it's decay. So here we see that we're at 1.07. So this represents that this is a growth function. And we know that the percent rate of change, how far away am I from the value of 1? Is 7%. Okay, it's 0.07, which means 7%. Okay, I'm growing at a rate of 7% each, whatever it is. In this case here, we can see that we're below 1. So because we're below 1, this represents a decay function. And again, you want to think to yourself, how far away am I from 1? That distance from 1 represents the percent rate of change, because 1 is like your basic constant number. So if you're at, say, 0.8, that would mean you're decaying at 20% because you're 20% away from 1. If you had 0.5 there, you would be decaying at 50%. If you had 1.5, you would be growing at 50%. So it's how far away you are from 1. In this case, 1 minus 0.98 is equal to 0.02. So we're decaying at 0.02, which is 2%. So our percent rate of change here would be a 2% decay, okay? 2% decay here because we're going down by 2%. So you always want to think, again, like I said, as how far away are you from 1 in terms of that percent rate of change. And remember, above 1 is growth, below 1 is decay. We're not going to worry about example 3 here, rewriting the exponential function to determine if it's exponential growth or decay. And these examples 4 and 5 we'll look at in class. Next thing in here is something that's referred to as compound interest. So again, it's an application of the exponential function rules, but now we're doing something a little bit different here. We're adding a couple moving parts in here. We've got these things called n, okay? So compound interest is the interest earned on principal and on previously earned interest. The balance y of an account earning compound interest is given as the formula below. So it looks very similar to what we saw, except now, like I said, we have these n's that are coming into play as well. So P, instead of using A, we now use P because we're talking about banking terms, represents the principal, which is just the initial amount. R is the annual interest rate, again as a decimal. T is time. And then N is the number of times the interest is compounded per year. So this is a very important application. You go to the bank, you invest money, they tell you your interest rate is 1.3%, compounded monthly, compounded annually, compounded quarterly, compounded weekly, whatever it might be, okay? That N represents how many times over the course of a year your interest is compounded. So for example, if it says it's compounded quarterly, your N would be 4 because it's compounded 4 times in a year. If it says it's monthly, your N would be 12 because it's compounded 12 times in a year. If it said it was weekly, how many weeks are there in a year? 52. Then your N would be 52, okay? If it said semi-annually, it would be 2, okay? Depending on what it is, N represents how many times during the year your interest is compounded. So again, make sure you have this formula down. Make sure you know what each of these are, P, R, T, and N, as we see these types of examples. So let's look at one. You deposit $100 in a savings account that earns 6% annual interest compounded monthly. Write a function that represents the balance after T years. So again, we're looking at our formula, y equals P, and then in parentheses, 1 plus R over N raised to the NT. So y equals P, then in parentheses, 1 plus R over N raised to the NT. So what is P? P is our principal amount. P in this case is $100. That's how I'm starting with. What is R? R is 6%. So 6% as a decimal is going to be 0.06. What is N? Well, if it's compounded monthly, N is equal to 12. Okay, because there's 12 months in the year. So let's write our equation. Y equals 100 in parentheses, 1 plus R, which is 0.06, over 12, raised to the N, which is 12, T. And I don't know what T is because it hasn't told me. If you want to divide that 0.06 over 12, you certainly can, but it's perfectly acceptable to just leave it like this. And again, all I'm doing here is I'm just plugging in values into my function to determine what it's going to be. If it said, what's the balance after 50 years? I'd plug in 50 for T, and I'd get my solution. We'll save example 6 for class. As well as example 7. You've got the foundation for exponential growth and decay, and we'll see you there. Have a nice day, guys.